Hello, my name is Ari Rubenstein, and today I'll be talking to you about how we can design trajectories that are resilient to missed thrust events using expected thrust fraction. This work is part of an ongoing collaboration between the Astrodynamics and Space Research Lab at the University of Alabama and NASA's Jet Propulsion Laboratory. In this talk, I want to answer three main questions. What are missed thrust events? How do we embed these missed thrust events into the deterministic optimal control problems? And then what are the effects of the embeddings on trajectories, both qualitatively and quantitatively? Electric propulsion is an enabling concept for many new deep space missions. Unfortunately, their limited thrust output increases the duration of thrust arcs from minutes to weeks or even months at a time. There's a 60% likelihood that a spacecraft enters a safe mode every 200 days. Mars 2020, which launched just 2 weeks ago, entered into its first safe mode only 3.5 hours after launch. During these safe modes, the propulsion systems are generally deactivated, so if a safe mode overlaps with a thrusting arc, this is the start of a missed thrust event, and a 10-day missed thrust event can cause a mission delay of 200 days or even cause the complete loss of a mission. The problem isn't just a single missed thrust event. If we look at a graph of the number of missed thrust events and the probability of occurrence on a 1.1 year trajectory, we can see that the likelihood of one missed thrust event or two missed thrust events is greater than the likelihood of no missed thrust events. Furthermore, the cumulative probability of two or more missed thrust events is greater than 50%, meaning the question is not just, will there be a missed thrust event, but how many missed thrust events and what will we do about it? In 2018, Imkin and a few others at the NASA Jet Propulsion Laboratory looked at simulating these safe mode and missed thrust events, and they found that the time between missed thrust events and the missed thrust event duration both followed Weibull distributions. And as you can see from the bottom here, the Weibull distribution is a two-parameter distribution determined by both its scale and its shape, which tells you whether it is more likely over time or less likely over time. Now, let's turn to what is expected thrust fraction. Writing out a very general optimal control problem, we have our cost function that we're trying to minimize and our dynamics that we have to obey. Now, in this case, because missed thrust events are stochastic in nature, we've wrapped our dynamics with an expectation operator. And because of the linear nature of both the integral and the expectation operator, we can pull the expectation inside the integral and then just take the expectation of our dynamics. The dynamics for this problem are going to be two-body planar motion with low thrust, so we have our very traditional two-body planar terms and our little thruster term. The only thing that's new about this formulation is this aleph right here, and also over here and over here in each one of the thruster terms. And this aleph is a random variable that's 1 if there is no missed thrust event, and it's 0 if there is a missed thrust event. Taking the expectation of each of our equations of motion, we can see that because most of the terms are not random variables, these are all deterministic variables, and aleph is our only random variable, we just need to take the expectation of the aleph. And thanks to the work of Imkin et al., we know that aleph is just a function of time and not of state, which means we can pull the expectation of aleph out, and it is a separable subproblem that can be done offline. We developed an integral for the expectation of aleph, where aleph is a function of tau, which is the time since the last missed thrust event. If you want to know more about how we developed this integral, we write about it in detail in the corresponding paper to this presentation. We can then numerically integrate this function, and we get this curve in the upper right-hand corner. We then chose to fit an 11-term approximation to this integral, and we overlaid it as the blue curve over here. And you can see that it matches up with the red curve, the numerical integration, quite nicely. And this approximation, this 11-term approximation, has some really nice properties. First of all, it's smooth and continuous for whenever tau is greater than 0, which makes it really nice in a gradient-based optimizer. And last of all, it's very well behaved. So the maximum error is 1.5%, and that comes right around here. As tau goes to infinity, the error goes to 0. Now that we've talked about what are missed thrust events and what is expected thrust fraction, let's apply it to a specific problem. And the problem we're going to apply it to is a low thrust trajectory from Mars to Earth. And both Mars and Earth are going to be in circular planar orbits. We're going to use two-body dynamics and polar coordinates. Our thrust will only be able to put out a max thrust of 1.3 newtons, and we're going to maximize the delivered mass. Now our spacecraft will have two control variables. Its thrust, which is u, and the in-plane control angle, beta. For the Mars to Earth trajectory, for a 1.1 year time of flight, the spacecraft starts at Mars, goes around, comes in, and arrives at Earth. This trajectory was optimized using a direct collocation method. Now, if we design a nominal trajectory and an expected thrust value trajectory, both of them for the fixed time of flight are completely bang on for the thruster, so the thrust is always on for the entire trajectory. The only difference is in the in-path control angle, beta. But if we plot it out right on top of each other, we can see that both the deterministic trajectory and the expected thrust fraction design trajectory are nearly identical. So by taking the difference between the two of them, which is the deterministic minus the expectation, we can see the difference in control. So the thrust, because both of them are bang on, the thrust fraction difference is 0 for the entire trajectory. But the difference in control is negative in the beginning and positive in the end. And it goes through this little switching time right around 180 days. If the trajectory was both positive before the switch and after the switch, the trajectory would just be, expected thrust fraction would just be shifting the trajectory left or right. But because it's negative in the beginning and positive in the end, we know that it's doing more complex work than just shifting the trajectory. If we then free up the time of flight, we get two more interesting results. The first is that the expected thrust fraction design trajectory takes longer to arrive. The second is that expected thrust fraction is delaying the major angle changes in the trajectory. It's hard to see here, but the expected thrust fraction trajectory is just below the deterministic thrust fraction trajectory in the beginning. To make this a little more apparent, let's introduce the concept of modified expected thrust fraction. And it's just the normal expected thrust fraction we've seen before, but now we have this user-defined variable nu, which determines how conservative our modified expected thrust fraction is, and we're multiplying that nu by the standard deviation of expected thrust fraction. And if we have a nu of 0, that corresponds to this expected thrust fraction curve right here. But as we increase nu, the expected thrust fraction becomes more and more conservative. Additionally, if we go to a new value of negative 0.1, we can see that we have basically returned to a traditionally designed trajectory. So now using modified expected thrust fraction for a fleet's free time of flight Mars to Earth trajectory, we can see that as we increase the new value, the beta actually flattens out in the beginning, in the middle, and it starts to push towards longer trajectories in the end. And if we look at our model diagram in the upper left-hand corner, we can see the beta value at this 100-day mark represented right here. So it's thrusting opposite the velocity vector, which is what we would expect when going from a higher circular orbit to a lower circular orbit. Now if we start looking at now that we've looked at the qualitative changes that expected thrust fraction makes to the trajectory, let's look at the quantitative changes it makes to the trajectory. So we're going to remain in the Earth to Mars trajectory transfer with a free time of flight. And if we just look at expected thrust fraction versus the traditional trajectory, using expected thrust fraction decreases lateness by 47.6%. It decreases the mass delivered by only about 0.4%, but the success rate is increased by 4%. What's more is if we use modified expected thrust fraction, so traditional expected thrust fraction, which is over here, has a success rate of 65.4%. But if we use a new value of 2 with modified expected thrust fraction, that success rate increases up to 95.8%, which is a major increase in the success rate for only about an 800 kilogram decrease in delivered mass. So, in conclusion, we can use expected thrust fraction to improve trajectory resiliency, and we get a large improvement in the success rate for only a small loss in delivered mass. Additionally, the lateness and success rate, along with the mass delivered, can be traded upon between to ensure that the mission is tailored to the specific risk tolerances of the engineers designing it. Finally, we've also developed a closed-form approximation for expected thrust fraction. So the entire design process is now deterministic. You don't need to run a Monte Carlo just to design your nominal trajectory. In the future, we aim to apply this to a wider set of boundary conditions and expand this work to higher fidelity models. Now, if you have any questions, please join us in the Trajectory Design and Optimization number 5 working group, and that will be on Wednesday, August 12th, 2020. I will be personally there answering questions online at 3 o'clock p.m. Eastern Time. I look forward to seeing you there.